Dear students, now I am discuss about the continuous distribution of charge. In the previous lecture, I have discussed about quantization of charge. Actually, I have discussed there about certain properties of electric charge, and one most important property of electric charge actually, the quantization of charge. That is, the charge of a body is a integral multiple of electric charge. That means the charge involving a body is actually discrete distribution. But here I just want to discuss about the continuous distribution of charge. So the two things are actually contradict to each other, because in the properties of charge I have discussed about the discrete distribution, that is, the charge is the integral multiple of electron. But here I have discussed about the continuous distribution of charge. These two things are contradict to each other, but this contradiction can be solved by saying that one is the microscopic phenomena and another is the macroscopic phenomena. When you talk about the microscopic phenomena, then in the microscopic viewpoint we have to discuss about the quantization of charge. But when we talk about the macroscopic viewpoint, then in that case we have to discuss about the continuous distribution of charge. This is actually because of the fact that when you talk about a small amount of charge, then even the charge is small, but the number of electrons involving that charge will be very large. That is, in a very short or in a very small charge, there is a large number of electrons. So the electron density is very large, that we can assume that the charge is distributed continuously. And that is the macroscopic viewpoint actually. If we take an example, the phenomena will be clear for us. Let us take a very small amount of charge, that is Q equals to 1 microcoulomb. When you talk about this 1 microcoulomb charge, so the number of electrons involving this 1 microcoulomb charge will be very large. This is a very small amount of charge, that is 1 microcoulomb. That is nothing but 10 to the power minus 6 coulomb. But if we talk about the number of electrons involving this charge, that Q is nothing but Ne, which is 10 to the power minus 6. So this N is 10 to the power minus 6 divided by E, and E is 1.6 into 10 to the power minus 19 coulomb. So the 10 to the power minus 19 and 10 to the power minus 6 will be 1 over 1.6 into 10 to the power 13. So there is 10 to the power 13 number of electrons. That is the huge number of electrons involving the 1 microcoulomb of charge. So the electron density is very large. That's why we like to discuss about the continuous distribution of charge in some cases. But this distribution of charge, that is continuous distribution of charge, may be of three types, and it depends on the values, it depends on the distribution of the dimension of the body. When this charge is distributed along one dimension, that is along a line, then we have to discuss about the linear charge distribution. And when it will distribute along a surface, then we have to take about the surface distribution. And when it distributes along a volume, then we have to discuss about the volume distribution of charge. So the very first topics we want to discuss about here is the linear distribution of charge. So the very first one is linear distribution of charge. Now, if we talk about that is a line and the charge is distribution along this line, and let me consider the length of this line, this linear conductor, let me say, and this is the length is L, and total Q amount of charge is distributed along this line. In that case, the charge per unit length is nothing but the linear charge density. So here, if we talk about this linear charge density, this is lambda, which is nothing but charge per unit length, that is Q by L. Now, when we talk about the distribution of charge, this is lambda, if this lambda is not uniform, here the lambda is uniform because per unit length the amount of charge will be same. But if this is not constant, then we have to discuss about the charge distribution or the linear charge distribution for a small element, and let me consider the small element is dl. If the small element is dl, in that case this lambda will be dq over dl, and in that case if we talk about the total charge of this line, then that will be q, which is integration dq, and this integration dq is lambda dl. So that will be the line integration along the line. So this is actually the linear charge distribution. Now if we talk about the surface charge distribution, that is when the charge is distributed along the surface. When the charge is distributed along the surface, in that case we have to discuss about the surface distribution of charge or the surface density of charge. Surface distribution. In that case, the charge is distributed along the surface of S. Let me consider that Q amount of charge, total Q amount of charge is distributed along the surface S. In that case, the surface density of charge sigma is nothing but Q over S. But for non-uniform distribution, this sigma can be written as dq by ds, and in that case dq is nothing but sigma ds. So the total charge q is actually integration dq, that is integration sigma ds, that is the surface integration. Similarly, if we talk about the volume distribution of charge, let me consider that there is a volume V and a charge of Q is distributed along this volume V. In that case, the volume charge distribution, we can write down over here the number 3, that is volume distribution of charge. And here the volume density that can be written as rho, which is nothing but Q over V. Similarly, for non-uniform distribution, we can write down rho equals to dq by dv. So dv is nothing but dq is nothing but rho dv. So the total charge, that is q, is integration rho dv, that is the volume integration. So there are 3 types of charge distribution, as we have said earlier. But if we take a certain configuration of this line, of this surface, of this volume, then we will get a standard expression for this charge distribution of 3 types. If we talk about the linear charge density or the linear charge distribution along the circumference of the circle of radius r, then the lambda will be nothing but q divided by L, and here L is 2 pi r. So lambda can be written as q over 2 pi r. Similar case, if this is the surface of a sphere of radius r, then the sigma will be q divided by s, then that will be q divided by 4 pi r square. And similar for the volume charge distribution rho, q divided by v, and that is q divided by 4 by 3 pi r t. Okay, thank you.